尊敬的评委老师还有各位老师，今天下午好，我是来自马来西亚的徐英野。今天我要谈我关于基于机器学习的离子电池健康预测和充电优化策略研究。Good afternoon, everyone. I'm Yin Yi from Malaysia. Now I'm going to talk about my research on lithium battery, health prediction, and charging optimization strategy based on machine learning method. First of all is the research content, which across background, trend, framework, content, and future work. Okay. According to UNEP, the global Earth temperature are at rise. It can be increased in around 2.6 degrees Celsius to 3.1 degrees Celsius this century. These have caused an issue to the global climate change and pollution. Besides, the energy security have been concerned to global Earth. The global Earth have been relying on petroleum as major energy source. However, the region conflict in Middle East, which amplify energy instability, highlighting the vulnerability of relying on single source energy. Therefore, it leads to the widespread application of lithium-ion battery in EVs. Lithium-ion battery in EVs are very widespread due to its long cycle life, high energy density, and fast charging speed. Many political unions, such as China, have emphasized EV development and stable energy supply chain across its recent 3-5-year plan in the 21st century. Besides, European Environment Commission has now planned to expand EV charging infrastructure and installation. There are few strengths and challenges applying lithium battery in EVs. First of all is the low carbon emission. By applying lithium battery in EVs, it enables the transition from fossil fuel vehicles to electric transportation, and it can integrate with energy system which support sustainable energy development. Besides, it can support long cycle life, which it provide high energy density and long cycle life, which is suitable for EVs. It can enable the extend driving range and reduce the frequency of battery replacement. Last but not least, it has the fast charging capability. It supports fast charging and can be configured to meet different power and energy demand. It is flexible to adapt and etc. However, it still faces several challenges in the world. First of all is the data modeling in real world. Real world data are often very noisy, incomplete, and highly variable, which limits the accuracy of health prediction model. Besides, lithium battery suffered from performance degradation in terms of capacity fade and internal resistance increase. Last but not least is the cell inconsistency. The battery cell have to be connected together at 100 something to support enough energy demand and power supply for the vehicles. However, every single cell in the battery pack have different variable and inconsistency in terms of voltage, temperature, and degradation. These were challenges and also complications for management and control strategy. Therefore, designing a reliable lithium battery pack BMS for real-world operation is essential for stable and efficient operation. Next is the research trend. For battery health prognosis, it can be generalized into three types, which is experiment-based, model-based, and data-driven. The experiment-based assess battery health prediction and modeling by directly measure the gradual decline in terms of capacity and power and etc. One of the examples is the EIS, where for model-based, it approximates the dynamic behavior within a lithium-ion battery cell by constructing a specific physiochemical representation for its internal process. One of the examples is the ECM, which you can construct in 1RC and 2RC. The last one is the data-driven method, which leverage operation and historic data to model and predict battery degradation without relying explicitly on physical or electrochemical models. Some popular models such as LSTM, transformer, are popular models in data-driven. However, these three methods still suffer. They have their own strength and also their own weakness. First of all is the experimental base. It can directly measure the measurements, high integrity, and have insight into degradation mechanism. However, it requires long-term cycling experiments, and it's time-consuming and limited real-world generalization. But for model-based method, it is a mechanism-based method which we can understand the battery internal mechanism in terms of resistance and capacitor. However, it's sensitive to parameter and its computational complexity. Last but not least is the data-driven method. Data-driven method, one of the most strengths it has is to capture the non-linearity of the battery, and it's also flexible for large data set. However, it usually relies on data quality and quantity. It has limited interpretation, and also it has generalization challenge. In this research, data-driven is the focus of the research because it is effective in modeling the complexity and variability of real-world operation. And then the data-driven battery model health prediction can be generalized into these three processes, which is the data augmentation method that focus on the input data quality. The middle one is the health prediction model, which focus on the health prediction algorithm itself, and also what we do with the data after we prediction. We need to control it. So this is the charging strategy control. Let me have more insight into it. The data augmentation method focuses on two levels of the data augmentation of the data. First of all is the SOC level, which acts as a parameter identification, such as FFRS, but more about using data-driven method. And then, after we augmented the parameter, we have the cycle level, which we generate virtual battery. By generating virtual battery, it improves the data quality and improves the performance of capacity estimation or SOH estimation. Where for health prediction model, it focuses on the algorithm of health prediction itself. Traditionally, we use support vector machine and etc. to estimate the battery health prediction. But recently, the improvement and enhancement for the model prediction is also a key investigation and research for the current research. One thing is about SOH prediction and also the lithium-ion pack inconsistency that we need to consider. Last but not least is charging strategy control, which we utilize the predicted result for the battery. How are we going to do it? We can use charging control because charging is one of the most critical influencing factors that affecting battery degradation. And strategy control for lithium battery include the charging control method and also multiple objective optimization. By these three processes, it provides a comprehensive lithium battery pack health prediction and charging optimization strategy, which is my thesis title. Let's talk about data augmentation. Data augmentation, as I mentioned, can be generalized into SOC and cycle level. The SOC level focuses on parameter identification, which applies several methods such as PSO, Kalman filter, RLS, FFRS to improve the battery parameter in terms of modeling it. Normally, we'll model the battery using electrochemical methods such as equivalent circuit model ECM in terms of 1, 2 RC, and then we apply the FFRS to do parameter identification. This is the SOC level. After that, the high level is the cycle level, which we improve the battery health feature extraction by using several methods, which is wavelet transform, dynamic time wrapping, and GAN. By using this method, it can generate virtual battery, which can be used later that when we are doing health prediction model. However, the current research on data augmentation still faces several limitations. First of all is the lack of physical consistency. Augmentation method generate data that fit statistical pattern. However, it sometimes violates the physical condition, violate the electrochemical constraint. For example, the data should have SOC from 0 to 100, but it might generate the data that it not belongs to the range because it's not following the physical constraint. So this is one of the examples, one of the weaknesses. The second one is the poor real-world generalization. Most augmented data are derived from control lab dataset, which fail to represent highly dynamic real-world usage. The third one is the limited degradation diversity. When we are doing GAN or data augmentation, it always have an issue called model collapse. Model collapse means that we try to generate data which is safe, but it's not diversity enough. For example, the data should degrade differently, but it do not capture it because the model wants to be safe in terms of statistically. This is also one of the limitations that we are doing data augmentation. Last but not least is the high computational dependency. Several approaches that is applied by researchers such as quantum-based method, deep generative model, require heavy computation or prior experiment calibration, which is a high computational for the researcher. Therefore, here comes to our first scientific problem. A robust data augmentation method to create virtual batteries that expand data diversity and simulate rare condition is needed. Okay, next talk about battery health prediction model. First of all, we need to understand the workflow of battery health prediction model. It normally undergoes data cleaning, which we try to clean the data in terms of outliers and also remove data which violate physical explanation. And then we do feature extraction, which we extract, transform raw battery data into meaningful health indicators. It has generally two types, mechanism-based and also machine learning-based, which I will discuss later. And then the feature that's extracted, of course, have to be correlated with the SOH and the battery capacity degradation. And then we use a battery health prediction model, which is normally modeled as SOC, SOH, and etc. to evaluate the battery status. It focuses on performance degradation of battery based on capacity and internal resistance. But of course, some researchers also model the battery SOH based on energy developed and also loss. Let's talk about feature extraction. There are one main issue of feature extraction is about cell inconsistency. There are two types of feature extraction method, which is machine learning and mechanism-based. Machine learning-based learn the machine features from historical data. Some of the examples are CNN, PCA, and LSTM. It is flexible, but normally it high computational cost and often black box. Wherefore, mechanism-based, such as ICA, DVA, incremental capacity analysis or DVA, it has strong integration. However, it often has difficulties in real-world application because the data is incomplete. These two methods for current research overlook one important thing that I said, cell inconsistency. The cell inconsistency among individual battery health in terms of voltage, temperature, and degradation level complicate the health prediction model. The cell-to-cell variability frequently stems from inconsistency introduced by the manufacturing welding process, and the modeling of cell inconsistency is yet to discover. Therefore, and then is the battery health prediction model, which is SOH prediction model. By using machine learning method, it normally leverages the historical data to estimate the battery SOC and SOH. This is the timeline of SOH prediction recently by the trend. 10 years ago, people focused on traditional machine learning method, such as support vector machine. This relies manually on engineering features, and it learns a mapping between these features to SOH. However, it does not learn features automatically. And then people investigate about ANN, artificial neural network, which learn non-linear relationship between input features and SOH. However, it also depends a little bit on manual features and have limited ability for time series learning. Recently, people focus in advanced feature learning methods such as LSTM, GRU, transformer. The main difference is will automatically learn the battery features and then try to capture the time series data on it. However, this method still suffered from long sequence forecasting problem, which is one important thing that we have to discover for battery health prediction model. Therefore, it comes to a conclusion about the limitation of battery pack prediction. First of all, is the battery cell inconsistency. The battery cell inconsistency is yet to discover, like I mentioned in previous slide. And then it has poor real-world generalization for real-world SOH estimation, because the real-world features besides the battery itself, it also has some external environment factors, such as temperature, road condition, driving behavior, which is not very considered in terms of battery SOH prediction. And then it's the long sequence forecasting problem of current neural network. For example, a transformer. The transformer utilizes a tension mechanism to capture the battery relationship. However, it still has some limitation in terms of capturing spatial and hierarchical relationship. Last but not least is the retrained computational cost. Some of the model, when you try to use it in a different vehicle, different scenario, you have to retrain it again, which is actually very computational expensive. Therefore, it comes to the second scientific problem we have. An accurate robots and generalizable machine learning method integrated with transfer learning is essential for real-world dynamic battery pack health prediction. And then we talk about battery charging control strategy. The battery charging control strategy can be generalized into two types, model-free and model-based. Model-free charging use measured data and feedback to guide charging without relying on battery modeling. It is high adaptability but have limited interpretability. One of the examples is the CCCB charging, which we charge the battery by constant current and then constant voltage at the end. Where for model-based charging, it constructs the battery model by using a physics-based battery model. It has strong explanation and have machine learning interpreting. However, it often requires accurate battery modeling and is computationally expensive. One example here is the semi-empirical model, which is a model that shows battery charging degradation proposed by John. The research focused on model-based charging because it combines the physics interpreting with the adaptive control capabilities when we are applying control strategy. However, the current research on battery charging control strategy still faces several limitations. First of all is the aging mechanism limitation. Battery degrade are not using a single source of battery degradation mechanism. For example, you have LLI and LAM for the battery degradation, which is the loss of lithium-ion and lack of active material. Current charging method unable to effectively capture this underlying battery aging mechanism, which this should be act as a physics informed for battery charging. And then is high experimental demand. For this semi-empirical model proposed by John, this actually requires multiple experiments under different operating conditions to extract the constant for the formula, which is the activation energy and pre-exponential factor. It has to be done with different charging current and different charging temperature to extract these two constants for each battery, which is high experiment cost and demand. Last but not least is the adaptive charging challenges. It is challenging to develop a charging strategy that can adapt to different charging demand. For example, if the client wants to have a fast charging, or he wants to have a safe operation charging, which minimizes the battery temperature risk and also degradation. So we need to have an adaptive charging control. Therefore, it comes to the third scientific problem. A robust, flexible, and cost-efficient multiple objective charging control strategy is required. Okay, next we talk about research framework. The research framework map between the scientific challenges and also the research framework and the research content that I have. First of all, there are three challenges that we mentioned just now, and each chapter are linked with them. The second chapter, which is data augmentation and electrochemical parameter reconstruction, is aimed to challenge and mitigate the scientific challenge, which costly acquisition of battery state parameters and incomplete data profile. It do data augmentation across SOC and cycle level. And then the virtual battery is fed into a capacity estimation model, which is LSTM, to evaluate the performance of virtual battery. And then the third and fourth chapter try to mitigate the complexity of real-world EV operating factors. And then for chapter 3, it combines the hierarchical feature extraction method and also CNN transformer for battery SOH estimation and prediction for real world. But for chapter 4, focus on transfer learning method. In chapter 4, it includes the driving behavior classification, which I propose a method to classify the battery driving behavior and then transfer learning based on the classification. And then the fifth chapter focus on the charging control. I propose a multiple objective charging optimization strategy, model the battery degradation using machine learning method. For example, for the battery chapter 3 and 4, I use machine learning method to model the capacity loss. And then I use the similar model, which I learned from chapter 3 and 4, as the capacity loss model in chapter 5. And then this chapter 5 is the optimization method across capacity loss, thermal model, and charging time, which later I use a COPYA as optimization function. By using this method, the comprehensive research on lithium-ion battery health prediction and charging optimization control transform the initial scientific challenge from highly nonlinear, poor generalization, limited interpreting, and costly experiment into robust to noise, long life cycle, stable performance, and consistent accuracy. Let's talk about my first work. It's about data augmentation and electrochemical parameter reconstruction. Like I mentioned, the SOC and cycle level and the capacity estimation. First of all, a parameter identification or parameter reconstruction is undergo in SOC. I propose a transformer-based method to do parameter reconstruction for batteries to RC ECM model. And then for cycle level, I generate virtual battery as a data enhancement for capacity estimation model. In this case, the augmented data is the battery features which extract from incremental capacity analysis, ICA, as an augmented parameters. And then I propose a novel data augmentation method, which is W time gun, which modify on top of time gun for generation of virtual battery. After I generate the virtual battery, I feed it into the capacity estimation model, which I apply LSTM for batteries capacity estimation. The reason that I feed it into the capacity estimation model is to evaluate the performance of virtual battery that I generated. If the virtual battery is generated well, then I can improve the capacity estimation of the battery. Of course, how do we know the performance of battery? We apply an MMD, which I will discuss later. First of all, is the transformer-based to RC ECM augmentation. This formula shows the second order RC ECM, which I utilize a pure electric heavy vehicle experiment data. And then initially, it has its own 2RC parameter modeling. And the factory used HPPC experiment to evaluate and identify the performance and the parameter of these 5 augmented methods. So my method is to use transformer-based to augment these 5 parameters from 2RC ECM. Traditionally, people use FFRS to do parameter identification. So of course, I will compare the performance of transformer-based method with the FFRS. You can see, this is the result by comparing TBA and also other augmented methods such as LSTM, MMN, GRU, and also the traditional method RS for FFRS. It is having 2 cases. The first cases utilize 20% of the data, which we feed more data into the network. The second cases only utilize 10% of the data, which means I use 10% of the data to reconstruct the 90% of the data. And of course, since case 1 have more data fed into the network, case 1 have higher accuracy than case 2. However, in both cases, the proposed method, transformer-based augmentation, outperform everyone. As compared to the traditional FFRS, this method can improve the accuracy by reducing CMAE by 62.27, CMSE by 86.47, and CRMSE by 61.5. But if I compare with LSTM, it is 30% better than LSTM. So it proves the robustness and accuracy of parameter reconstructing in SOC level using transformer-based method. And then is the virtual battery creation. After the SOC level, we focus on the cycle level, which I aims to generate virtual battery on the cycle level using W time gun. So what is W time gun? Time gun, first of all, time gun is the method proposed by SOO YIN on 2019, which is a time series augmentation method. However, his method has some limitation. First of all is the cost. It is using gun cost as the evaluation of the model. However, gun cost is the cost that will generate data statistically fulfilling with the original data. But this data, like I mentioned, is not diverse enough. That's into Washington loss to generate diverse battery data. What is Washington loss? Washington loss is a very interesting parameter which can evaluate the diversity of the data, and also where I use MMD as another method, as 2 method evaluator to identify both the battery diversity and also accuracy. So by using ICA as HF feature extraction, I extract 6 feature extraction from ICA, and I feed it into W time gun, which is the novel W time gun of I propose. One thing is about MMD. What is MMD? MMD is another evaluator different from WC, which can evaluate the battery statistically different. The higher MMD means the more different the battery data compared with the original battery data. So by proposing MMD, it acts as an evaluator to check whether the battery generating good enough. Is it a well-generated virtual battery or poorly generated virtual battery? For the battery that is poorly generated, I propose, of course, to remove it from the capacity estimation model. This is because they generated poorly, and also they should not add into the capacity estimation model. Of course, I compare it with adding or not adding to prove the conclusion and review of this method. First of all, I compare time gun and my W time gun in terms of battery 1 and 2. For battery 1 and 2, we can see that W time gun has outperformed the traditional time gun by 86% and 70% for WC and 98 to 97% for MMD. Why is it happening? Because of the converge issue and the data WC gun loss itself. For traditional time gun, it used a dump as optimization function and also gun loss as cost function. In my proposition, I use a Washington Gauss as the cost function and also SGD as optimizer, which I mitigate the issue of converge issue for the network. And it turns out it performs better and generate better virtual battery. I of course also generate a lot of battery, and it shows that W time gun can produce better battery quality compared to time gun in many cases. And then we talk about MMD. Like I mentioned, MMD should be an evaluator that evaluating the battery performance in terms of poor or bad. So I compare, if I add this badly generated battery into the network, for example, the estimate LSTM W time gun, or I can use removing it since it performed badly, the enhanced LSTM W time gun. So it shows that by applying MMD selection, which remove poorly generated battery, it increased the accuracy of capacity estimation model by 9.52 and 14.24 for battery 1 and 2. Okay, last but not least, let's conclude about this content 1. First of all, I address the challenges of prevalence of incomplete real-world data and high cost of experiment by using a parameter reconstructing method, which by using transformer, I don't have to do experiment for the battery to check the parameter of ECM to RC. I only do 10% or 20%, then I use transformer to augment and reconstruct the battery parameter. And then I also review and model the relationship between virtual battery generated and also the capacity estimation model. By using MMD selection, I shows that if the battery have a poorly generated MMD, it should be removed from the network. If you don't, then the accuracy will not improve that much. This review the methodology for generating highly fidelity digital twins of the battery. My second work is about transformer-based battery pack calculation in real world. The two limitations that I mentioned in previous slide is the battery cell inconsistency and the long forecasting problem. So how do we deal with the battery cell inconsistency? I propose a two-level feature extraction method, a hierarchical feature extraction method, which I use PCA for the battery cell modeling and data aggregation for battery pack level feature extraction. The extracted features are evaluated using GRC, Gray Relational Correlation. The features are fit into a health prediction model, which I do an ensemble learning of CNN and transformer. This is because transformer network have limitation in their attention mechanism. So by utilizing CNN, it can better in capturing the spatial and hierarchical relationship in the data, which I will show later. Okay, first talk about health feature extraction. Like I mentioned, I apply GRC for feature correlation. And then this is a two-level hierarchical feature extraction, which I use PCA to explain and model the battery cell. In this dataset, I use a huge dataset of real-world lithium battery, which have 152 battery cells in a battery pack. So if I fit everything into the prediction model, it will be very costly. And also I do not model the battery inconsistency. So how should I do that? I use a principal component analysis. For principal component analysis, before we start to do dimensional reduction for feature extraction, we need to check about the cumulative explained variance ratio. We need to understand how many attributes should I extract from the huge dataset that can explain 95% of the raw dataset. So you can see, this is the lithium battery pack data, the buses, and it has cell inconsistency growing. The maximum and minimum voltage growing as the operation of the battery. So by using PCA to do explanation, I realized that 6 components is needed to extract from the battery cell data to have 95% of the explanation. So I extract 6 of them, and then I compare the correlation between the PCA and also SOH. It shows that in terms of GRA, it has high correlation with battery SOH. So it successfully reduced 96% of the data input for the data. And one thing to highlight, I compare the PCA method with other methods such as CNN and also aggregation. The aggregation is very simple. I just do the average of the data and see is it correlated with SOH. And it shows that, of course, it's low correlation with SOH. Therefore, proven the PCA features that are extracted is highly correlated with the battery degradation. Okay, this is the health feature that I have, and then I fit it into the SOH prediction model, which I do an ensemble learning of CNN transformer. Based on my research, 1D CNN is a very good ensemble learning method which you can add before any machine learning model. It can improve the machine learning performance by extracting spatial and hierarchical relationship. Therefore, I use CNN transformer, which I combine together, and feed these health features into it to do SOH prediction. And the SOH prediction results are shown at here. You can see that I compare the CNN transformer with LSTM and also CNN LSTM, by LSTM, and etc. One thing to highlight here, by applying 1D CNN, the accuracy of every machine learning method improved. Not only transformer, GRU and LSTM also improved by 9.9 to 7.7. Of course, transformer improved by 9.8. This has shows that the proposed method by applying 1D CNN as ensemble learning actually helps to improve the model accuracy. And also one thing is about the informal network. Because that time when I'm applying transformer, informal network was kind of like very popular in the researching area, so I also apply it. However, the informal network do not perform good. It have a negative R-square. It means that it is very, very bad. It does not go to the real direction. So why is it? I also investigate in terms of informal network to better understand the machine learning model. The informal network perform badly because it is overfitting in modeling. Why? Because the data size, of course, is a long sequence data set, but it is long but not large. Therefore, the design of informer to be more aggressive and modeling the long, large data set is not very suitable in this case, since I have already used PCA to reduce the data set. Therefore, it is the aggressiveness of informal network for long forecasting problem have limits its application. And last but not least, let me conclude this research content. First of all, I address the challenge of modern lithium battery pack for inconsistency and real-world battery SOH prediction. I use a PCA method to do dimensional reduction, which jointly model the battery cell and pack level for feature extraction. And then I do an ensemble learning method which combines CNN and transformer for SOH prediction. I also proved that by applying 1D CNN, it improved the accuracy of most of the machine learning method, showing that it can capture the limitation of transformer network which cannot capture spatial relationship and hierarchical relationship. It proved that I have to do battery cell modeling, address the long sequence forecasting problem, and provide a robust real-world generalization. My third content is about transfer learning. First of all, what is transfer learning? Transfer learning allows knowledge acquired from one task without retrain from scratch for the model. Therefore, I propose a method of transfer learning based on driving behavior classification. In this data set that I apply is a data set of vehicles EV in Hefei, which the road condition is similar. Therefore, the only things that might affect the battery degradation externally is the driving behavior. How do I do that? I propose a driving behavior classification formula, which is the velocity per SOC. Why I do that per SOC? Because the driving sequence and battery discharge is random. You do not know they travel for 10 minutes or 1 hour. So the best way is to filter, smooth the data, and then provide a driving behavior classification based on velocity per SOC. Among all the data set, 4 vehicles has been addressed as aggressive driving, which is shown in the red color one. And also 4 vehicles has been shown as the moderate driving, which is shown as the blue color one. We can observe that obviously for aggressive driving, most of their time is in a high level, which is exceeding 100 ms. Where for moderate driving, most of the time it is below 500 ms. Of course, I also utilize this external environment as a transfer learning model evaluation. The transfer learning model that I propose is ETS transformer, which I combine the ETS decomposition of ETS former to transformer network. And I also add an FC layer. What is ETS decomposition? This is actually an innovation of ETS former. It represents the components which try to capture the level, trend, and seasonality of the dataset. And then FC layer. FC layer is very popular in transfer learning model, which everyone will add it to provide flexibility and enhancement. Of course, I also do an evaluation of FC layer to see if I add FC layer, is it better or no. The transfer parameter here, what things I have transferred is the hidden weight from the network, such as level, season, and trend. For those who do not have this level, season, and trend, they also have their own weight and bias for FFN, feed-forward network. For example, LSTM and GRU. I compare their performance, and also it shows that the proposed method, which is using DBC, ETS transformer, FC, have the best performance in terms of SOH prediction. But one thing very weird, the vanilla ETS former, which I use the whole structure of ETS transformer, the ETS former, it does not perform better than ETS transformer. Why? This one I'll talk about it later. First of all, we look at the DBC. So by using driving behavior classification, it actually improves the accuracy of every model. No matter it's ETS former, ETS transformer, LSTM, and etc. It proved that by integrating these external factors, which is driving behavior classification, can better improve the model prediction. You can see by integrating DBC as an for my proposed method, it reduced around 30% for the estimation error, proven the robustness and accuracy of proposed driving behavior classification. Let's talk about the other thing, which is the we compare to proposed method such as the other method like LSTM and also ETS former. The proposed method still perform better than the other model. And then it's the ETS former. Like I mentioned, the vanilla ETS former, they perform badly compared to ETS transformer. This is weird because the ETS decomposition I borrow from ETS former. This is the original idea from ETS former. So why he doesn't perform better than ETS transformer? This is because the exponential smoothing attention. One thing I do not utilize in ETS transformer is the exponential smoothing attention of ETS former. And by using this exponential smoothing attention, it actually slows down the accuracy, reduce the accuracy. This is because it do not model the battery in terms of monotonic behavior. The battery degradation is a monotonic behavior, but by using exponential smoothing attention, it do not smooth the battery monotonically in one direction. Of course, in the future, we can focus on giving physics informed into ETS format to enhance the performance of it, but right now, by comparing with the proposed method and vanilla ETS format, the proposed method still performs better. In conclusion, in this content, I introduced a novel transfer learning model based on driving behavior classification. I provide physical explanation to the model since I already giving it driving behavior classification. It can lead to high physical explanation, cost efficiency, since I'm doing transfer learning. My last research content is the multiple objective charging optimization strategy based on COPYA. The limitation that I mentioned in the previous slide is the aging mechanism limitation, high experiment demand, and adaptive charging challenges. To mitigate these three issues, first of all, for aging mechanism limitation, I investigate the battery degradation mechanism. You can see the battery LLI, lack of lithium-ion, is the main source of battery degradation in the beginning. And then LAM becomes larger and larger when we try to use the battery more. This is actually a physics informed for charging, which I will utilize it in my charging control. And then it's high experimental demand. Like I mentioned, the semi-empirical model, which you need to model the battery degradation during charging by doing a lot of charging experiments in different temperature and different charging current. So this is very expensive, so I use a machine learning method to model the battery degradation only based on limited data set, which can help to reduce the experiment cost. Last but not least, the adaptive charging challenges. By using an optimization control, modeling the battery degradation, thermal model, and charging time, it can help to leverage the charging control for user in different scenarios, which is safe and fast charging scenario. First of all, let us look at the objective function of charging optimization control. The charging optimization control across these several objectives. First of all is the capacity loss. I model it in terms of LI and LM. Both of them I use machine learning method, which is multi-layer per second. And then for the thermal model, it's very simple. I use a very simple thermal model, which I use the generated heat energy minus the dissipated heat energy. Last but not least is the charging time. The charging time, it serves as a cost function and also as a constraint to the charging optimization control. And then I will do a COPYA optimization later. First of all, let us look at the extraction of LI and LM. How do we extract the battery LI and LM? How do we know? So we can use DVA and ICA as a method to do extraction. For battery LI, it's the left shift of the battery in DVA analysis. Where for battery LM, it's the downward shift of the battery when we are applying ICA. So this method, we can model the battery LI loss and LI loss and fit it into a machine learning model. Like I mentioned, that's a degradation mechanism. Like the battery initially leads to more about LI loss and then LM loss. These have been fed into the battery during charging control. One thing, to evaluate the physics-informed effect of the charging control, I do an unbalanced SMLB. Unbalanced SMLB means that it's wrongly and arbitrarily weighting the drawn cost function, which is LAM, at its charging optimization control weight. And I compare this method with my proposed method. Before we continue, we talk about COPYA optimization. COPYA optimization is a really new optimization method which no one actually used it before for charging control. Why? Because they do not need to use it. Why? Because COPYA is a very good optimization control designed for constraint and non-linear objective. before me, most of the researchers, they model battery degradation using semi-empirical model, which is not a black box model. It's not a machine learning model. It have strong explanation and linearity. That's why COPYA is no need. You no need to use COPYA for optimization. But since I model the battery using MLP, it becomes a black box model. You have limited interpretation on this model. So most of the optimization method perform badly when they have a kind of objective which is black box. So therefore, COPYA comes. I compare the COPYA with the other traditional optimization method used in charging control, such as SLS, QPE, Truscon, PSO, generic algorithm. It performs the best. It has lowest time needed for optimization and lowest total cost. Therefore, it shows the robustness and the application of COPYA when dealing with this problem. And then this is the experiment setup, which I connect the battery testing system with the lithium-ion battery, and I attach a temperature sensor to the battery. And it has two scenarios, which is safe charging and fast charging. After doing the safe and fast charging, the proposed method shows lowest SOH degradation per cycle for the battery. Let's look at it more deeply. For safe charging, it has three things that I want to compare: the extreme temperature, the unbalance, and the proposed method. For extreme temperature, the weight focus on temperature instead of capacity loss, which of course leads to high degradation of the battery because it doesn't care. It want to charge the battery when it's as fast as possible and also safe as possible. Of course it's safe because the temperature range is not high, but then it leads to high degradation of the battery. And then is an unbalanced SMLP. Like I mentioned, LLI is the major source of degradation for the battery in the beginning, but unbalanced wrongly assign or disproportionately assign large weight on LLM loss, which leads to certain kind of degradation of the battery, but of course it's not higher than extreme temperature. But the proposed method outperform the other battery by reducing the SOH degradation compared to 1C CCCD by 26% and also the unbalance by 6.5%. This proves the effectiveness of physics-informed optimization in safe charging, which is able to balance LI, LM, and temperature. And then is the fast charging. The proposed method of fast charging also achieved the lowest SOH degradation. One very interesting thing about PI FMLP, it actually has very low SOH degradation. Why? Because it has lowest cutoff for CC and CD. It actually meet the objective that charge the battery as short as possible in CC and then low as possible in CD. Since the charging time is shorter, the battery degradation is shorter. So it actually meets many objectives like the fast charging and also the degradation charging for PI FMLP. Last but not least, by doing this work, I reduce the experimental burden, which initially people have to use semi-empirical model for doing battery modeling during charging. And I use a machine learning method which use limited data for battery degradation modeling. And I also use COPYA as an optimization method because MLP model is a black box model which traditional optimization method does not work that well. Last but not least, I successfully do and reduce the cost of experiment, physical explanation, and provide an adaptive charging control for battery. Here comes the conclusion and future work. This is a generally summary of what I've done. I focus on feature engineering, which I do data augmentation for the battery in SOH, SOC, and cycle level. Improve the data quality. I propose W time down for cycle level and transformer base for parameter reconstruction. After that, I feed it into the health prediction model, which I propose a hierarchical feature extraction and also CNN transformer model for battery SOH estimation. I also propose a real-world transfer learning method, which transfer learning based on driving behavior classification, and the ensemble learning, which is ETS transformer estimate, has proposed. Last but not least, I utilize the knowledge of me when I'm modeling the battery using machine learning method as the source of capacity degradation as one of the objectives of charging control strategy. And then I optimize it using Cognac. For future work, there's still some things that I think maybe I can do or the researcher can do. First of all is the integrated battery modeling. I mainly model the battery for its SOH in terms of capacity, energy, and etc. But I do not do a joint estimation of battery status, such as SOC, SOP, and etc. And I also think that the physical integrity still have a lot of things to do. For example, the cost function itself, I can construct a cost function which is more suitable for the battery model that is utilizing the physical characteristic of the battery. Last but not least is the advanced charging control. The charging control that I propose is a simple CCCV charging based on current. I think we can do fast charging or multi-state fast charging in the future. And last but not least, as during my PhD study, I have proposed 4 papers in Science Q1 as first author, and also many with my lab mates. And I also published an EI paper as first author, and I also award as the USTC Outstanding International Student Award 2 years ago. And then this is the thesis review comment, which I actually scored 88 and 89 for every one of them, 388 and 289, and I have modified my thesis based on the reviewer content. Okay, thank you everyone, and please ask any question. Thank you.